All right, welcome back to class. So the plan for today is to continue with and finish up binomial distribution, section 5.2, and then I'll post a YouTube supplement on Poisson distribution. So I think we're just going to kind of boot that to a supplement. You can watch a YouTube video on that. I think it'll be about 40 or so minutes long. I'll probably just take a chunk of a previous YouTube video and post that. So we'll boot Poisson. And then move on to Bayes' theorem. So I would like us to, uh, spend a couple of days on Bayes' theorem. I think it's not just Bayes' theorem, but really the ideas surrounding the Bayesian interpretation of probability, I think are really important ideas. So that will be what we'll continue on Monday, the 17th. And I mean, I say finish Bayes here. I feel like since we're finishing up binomial this class, we might not quite finish Bayes on Monday. It might carry over a little bit into Wednesday, but we should pretty much finish up Bayes' theorem on Monday the 17th. So that is our goal for the next couple of days. The quote of the day today, I actually kind of just saw this pop up on Facebook and was reminded of this one. So I think it's a good quote of the day. This is by Captain Jean-Luc Picard, played by Patrick Stewart, the legend Patrick Stewart, in Star Trek: The Next Generation. I think this was in like the first season. Um, and long story short, one of the crew members gets in a bit of trouble on a planet that they're visiting, and Jean-Luc Picard kind of delivers this line where he says, "There can be no justice so long as laws are absolute. Even life itself is an exercise in exceptions." And I think that's, often thought of as being one of the, uh, I don't know, most quotable lines or something in Star Trek, or maybe one of the most quotable, but least often quoted, or something along those lines. Um, and I think this touches on a lot of ideas. I don't know if it's as simple as just saying take this quote at face value and that it's true or anything like that. Um, there is in philosophy this idea called the trolley problem. You can look it up. Um, there are many versions of it, and it's very tricky because people will say, "Oh, this is the choice I would make," but then you reframe the problem to where it's basically the same choice in a slightly different context, and people make the opposite choice. So it's definitely not a clear uh, not a clear decision, I don't think. Um, and that touches on the idea of deontology versus consequentialism. You might, a philosophy professor would probably rake me over the coals for saying something like this, but you might think of like deontology and consequentialism as being two ends of a spectrum. One end of the spectrum is very much like by the book thinking, like these are the rules, we follow the rules, period of end of story. Almost kind of like mathematical thinking. So like a lot of math folks, maybe physics folks kind of tend to be on this side of thought a lot of the times, versus consequentialism, where it's kind of something more akin to the ends may justify the means way of thinking. The kind of rules are, meant to be guidelines, but can be bent. And, as a student, that when you're looking at the rules in a syllabus, if you're in a math or physics course, your professor is likely to be more by the book. That just tends to be the mode of thinking that pervades, these kind of fields. But if you're in, taking, say, a law class or something like that, they might be a bit more open to kind of bending the rules. So, uh, and this all really touches on also like what's the definition of justice? This is, we have an idea of justice system in the US or whatever, but what does justice even mean? It's quite tricky to define. If you say this is what I think I mean by a just system, or by justice being done, uh, often that's if you push the person, you ask a couple of follow-up questions. It's like, okay, you're not actually looking at justice there. Maybe you're looking at vengeance, or maybe you're looking at, protecting what's valuable to you or something like that. So these are all related ideas. So I think this quote really touches on a lot of deep ideas in philosophy, and really just ideas that are applicable to our society today as well. Like, what is our view on how rules are treated, what is our view on what does it mean for something to be just. It's probably not just something like there's a law written down somewhere, and if you follow the law, then that's doing something just. You know, we can all think of examples of where breaking the law might be what we consider the more appropriate action. So um, lots of interesting ideas, I think, that are touched on by this quote. Okay. Um, and yeah, if you want something to, think about, Google the trolley problem and, try to answer it yourself. What would you do? And then after you answer it, look up some of the variations of it and ask what you would do in those situations. And a lot of people end up kind of like answering effectively the same problem in different ways, depending on very slightly different contexts. All right, so in chapter 5, discrete probability distributions, we had introduced the idea of our first canonical distribution, the binomial distribution. And we said basically the idea was in 5.1, we said if I have just any probability distribution, discrete probability distribution, I know how to determine whether it's a probability distribution. Do the probability sum to 1? But then I know how to, say, compute the expected value with the formula or the standard deviation with the formula. That was pretty cumbersome, though, even for moderate length problems. And certainly for longer problems or for problems that where the numbers weren't as nice, basically, that would be quite an ordeal. One of the benefits of canonical distributions is we can group a bunch of distributions into a class. We can say any distribution that follows these four, or well, any situation that follows these four assumptions can be modeled by a distribution called the binomial distribution. This is a class of distributions that's parameterized by two parameters, n and p, the number of trials and the probability of success per trial. And in this class of binomial distributions, the huge benefit is that if I recognize a certain problem as being modeled by, say, a binomial distribution, and I can identify what are n and p, I could, for instance, compute any probability that I would like just using a formula. I just have to plug into this formula and it spits out the probability. I don't have to go back to my chapter 4 material or anything like that and really think through what should these probabilities be. I just plug into this formula and get the answer. I basically have done the hard thinking and analytical work once. I develop a formula from that, and then I can just kind of carbon copy that formula anytime that I need to use any of these distributions. And this is about where we left off last time, with our goal now being to find the expected value and standard deviation of a binomial distribution. Okay, so and just to recall, binomial distribution was something something where the process has a fixed number of trials with a constant probability of success for all trials, which we call P, and independence between trials. Also 2 outcomes per trial, but that's a bit more flexible than it might at first seem. And we are counting the number of successes on n trials. So the classic example is, say, the number of heads on 5 coin flips, something like that. Now let's consider a random variable that we're going to call a Bernoulli distribution. This is a binomial distribution with 1 trial. It's really that situation we looked at before where we can get a 0 or a 1, where we get a 1 with probability p and a 0 with probability 1 minus p. We looked at that in section 5.1. So that's really the situation that we're in here in a Bernoulli trial. This is just basically one flip of a coin. And we might note that x up here, counting the number of successes on n trials, the number of successes on n trials is really just the sum of n Bernoulli random variables. Right, I can think of if I flip a coin 5 times and count the number of heads, that's just like flip it once, write down a 1 or a 0, depending on whether I got it heads or not. That's 1 Bernoulli trial. Do that again, do that 5 times, and then add those numbers up, the zeros and the ones. So if I have a sum of Bernoulli trials, what would the expected value be? Well, the expected value of a Bernoulli trial we saw before was P, and its variance is P times Q, or P times 1 minus P. This is something that we saw in section 5.1. Okay, let's find the expected value of x of a binomial distribution. We might actually guess that the expected value is n times p if we thought about it for a little while. If I said, okay, flip a coin 10 times, and it's a fair coin, so n is 10, and p is 1/2, how many heads on average would you expect to get? And you'd say, well, I'd expect to get 5 heads and 5 tails. So where did that 5 come from? Well, that's half of the number of trials. That's the probability of heads times the number of trials that we're flipping the coin, number of times we're flipping a coin. If my coin was more biased towards heads, maybe I got heads 80% of the time. I say on 10 flips, how many heads do you expect? You'd probably say about 8 out of 10. Right? 80% probability of success per trial times 10, number of trials, that gives me 8. And we do, in fact, see that that is correct. There are times in probability and statistics, many times, where our intuition is not correct and we're a bit surprised. But here our intuition is correct. The expected value of the binomial is the expected value of the sum of the Bernoulli trials. But the expected value of the sum is the sum of the expected values. And since I'm just adding up n Bernoulli trial expected values, that's just n amounts of p added up. That's n times p. My expected value of a binomial distribution is n times p, the number of trials times the probability of success per trial. And the variance of a Bernoulli, variance of a binomial distribution is the variance of the sum of the Bernoullis by independence. And we had discussed before that when we have the variance of a sum of random variables, if those are independent, then we can rewrite that as the sum of the variances. So under independence, my variance is split apart like this. But each of my Bernoulli trials has variance PQ. So I'm just adding PQ to itself n times. And that gives me NPQ. And remember, this information about the Bernoulli trial, I mean, I wrote it out up here. Oh, why is that popping up like that? I wrote it out up here in more detail, but this stuff about the Bernoulli trial we did earlier in chapter 5. So you can refer back to that, or you can work it out with the chart as practice. That's not a bad thing to do. So the variance of a binomial is n times p times q, just pq added to itself n times. And therefore its standard deviation is square root of npq. So this is what's really nice about these canonical distributions. There are kind of, roughly speaking, two criteria to be a canonical distribution. One is it has to be a class of problems that is interesting, that comes up occasionally. And two, it has to be a class of problems where you can actually get answers reasonably easily. Right? So I can write down these formulas. My formulas don't have 1,000 different special cases or exceptions, or they're not super complicated to work out or to write down. These are pretty nice formulas, and there are a lot of things we want to model that turn out to be well modeled by a binomial distribution. So that's why we call it a canonical distribution, and it's widely used. So if I recognize that something fits the criteria for binomial distribution, I can figure out what is n, what is p, and then use these formulas, and I can get any probability that I want. I can get the mean and the standard deviation, basically just with a plug and chug, just plugging into a formula, plugging that in a calculator, getting the answer. So I've done all of the kind of statistical and probabilistic thinking already and calculations, and I've got formulas that apply to every member of this class of binomial distributions. Okay, so let's look at an example. So let's let x be the number of heads on 5 flips of a fair coin, and we want to find the probability distribution for x and its expected value as standard deviation. So we're going to do this kind of 2 different ways. One a bit more manually. Let me bring up the calculator. Hope we can clear that out. One a bit more manually. So we'll do maybe 1 or 2 of these probabilities by hand. And then we'll find the expected value of standard deviation by hand. And then we'll come over to Excel and kind of confirm our work. Okay, so looking at my setup, I see I have 5 flips of a fair coin, that's n. So I have a fixed number of trials. It's a fair coin, so each flip has probability of success or probability of heads, 1/2. So n is 5. P is 1/2, a consistent probability of success per flip. It's not like the probability of success, on the second flip is different than the first flip or something like that. There's independence. I think it's pretty clear that flipping a coin is independent. If I got heads or tails on the first flip, that doesn't really inform the second or third flip in any reasonable way. And each flip has success or failure. I either get a heads or I fail to get a heads. And then my random variable is counting the number of successes, the number of heads on n flips. So this does fit the model of binomial distribution with n equals 5 and p equals 1/2. So let's compute a couple of probabilities. Maybe we'll compute, say, probability x equals 1. What's the probability we get exactly 1 head on 5 flips? Be a little careful here. When we say the probability I get exactly 1 head on 5 flips, that doesn't mean 1 or more heads. And that also doesn't mean one specific sequence like heads, tails, 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 tails. The head can be in any of the 5 different places, so there are multiple ways to get this. But we just refer back to our formula up here. This is n choose k here. K is 1 for this probability that we're looking for. So I have 5 choose 1 times p to the k, or 1/2 to the 1. That's the number of successes, the number of heads, times q. If probability of success is 1/2, probability of failure is also 1/2 to the n minus k to the 5 minus 1, or 4. 5 choose 1 is just 5. Of the 5 different locations, I have to choose one. There's only 5 ways I could do that. I could choose the first, second, third, or fourth, or fifth. And then I get overall 1/2 to the 5th. Let me come over to my calculator and do 5 times, well, I guess I could do 5 divided by 2 to the 5th. 1/2 to the 5th is 1 to the 5th divided by 2 to the 5th, and 1 to the 5th, of course, is just 1. This gives me about 0.156 or so. What if I was looking, say, for probability x equals 3? Well, pretty much everything stays the same except for k. So I change n choose k, that second entry into the combination changes, and my powers change. So I get 5 choose 3 now instead of 1. 1/2 to the 3rd times 1/2 to the 5 minus 3, or second. Now here, 5 choose 3. There's lots of ways to pick 3 things out of 5, so let me actually use the calculator for this. I'm going to type in 5, go to math, over to my probability menu, I'll go left to wrap around, and then number 3 is the choose operation. So I do 5 choose 3, and I'd rather just hit enter here and then multiply by all of the other stuff. So that way I don't have to think about order of operations or where to put parentheses or anything like that. So 5 choose 3 gives me 10. and then I want to multiply by, I just hit times and it is going to take the previous answer, 10, multiplied by, well, 1/2 to the third times 1/2 to the second is 1/2 to the fifth, or I guess that's really just over 2 to the fifth power. And this is 0.3125. And I could do this for the others as well if I wanted to. I also can find the expected value of x, the expected number of heads on 5 flips. Well, that's just n times p, or 5 times 1/2 is 2.5. On any sequence of 5 flips, I'll never get exactly 2.5 heads, but the idea is if I ran this experiment, flip a coin 5 times, count the number of heads, write that number down, do that again, flip 5 more times, count the number of heads, write the number down, do that, say, 100 times, and I take this sample of size 100 and average it together, I would expect on average to get around 2.5 as my average. What about the standard deviation? The standard deviation is root npq, or np1 minus p, or that's square root of 5 times 1/2, this p, the probability of success, probability of heads, times q, or 1 minus p, probability of tails, is also 1/2 for a fair coin. Or this is root 5 over 2. My 1/2 times 1/2 gives me a 1 over 2 squared, but that's under the radical. That over 2 squared can come out of the radical as just an over 2. So if I do square root of 5, end the parentheses, then divide by 2, that gives me about 1.12 or so. So I have a mean of 2.5 with a standard deviation of just over 1. That means that, roughly speaking, again, if I'm kind of leaning on the empirical normal rule maybe a little more heavily than I ought to, but kind of roughly speaking, kind of reasonable results are anywhere between 2.5 minus 2-ish and 2.5 plus 2-ish, or somewhere between about 0.5 and 4.5. So in other words, kind of getting anywhere between 1 and 4 flips on 1 and 4 heads on 5 flips would, for a fair coin, would be kind of reasonable. Getting 0 or 5 heads on 5 flips of a coin seems to be like unlikely. Again, that's a very, rule of thumb heuristic kind of statement, but we know the kind of mean plus or minus 2 standard deviations is a very rough heuristic for non-outliers or for reasonably typical outcomes. Okay, let's look at fleshing out this table in Excel and then actually kind of manually, in a sense, computing expected value and standard deviation and make sure that we get something that meshes with these formulas up here. So here I'm going to have a column for K and a column for the probability. I have 0 through 5 as my options for K. Now for this probability, I could just put the numbers in like this, 1/2 and 1/2 and 5 and so on. But I think what I'm actually going to do is I'm going to put a couple of cells up top. I'm going to have n labeled here, and I'll set n to 5. Maybe I'll highlight these. And same with p. This n equals cell and this p equals cell don't actually do anything. They're just reminders to me what the cells next to them mean. So if I wanted to say right align this, maybe to make it look a little nicer. So the n equals cell and the p equals cell aren't actually doing anything for the calculation. It's just reminding me what I'm putting into D1 or in G1. And in D1, I put the number that I want for n, the number of trials, 5. And for G1, I want the probability of success, 0.5. I highlighted these in yellow. That's something that I sometimes do when I'm planning to change something. That kind of reminds me what I can easily change, what I'm kind of intending to be able to be changed, and what maybe is not so easy to change. Okay, so now if I want to compute these probabilities, I can do something like equals. Well, what's my formula over here? It's n choose k. The choose function in Excel is COMBIN for combinations. Remember, permutations versus combinations. And we see we want the number and the number chosen. So we do like almost like C N K in Excel's notation or syntax. So I want this number, comma, this number choose that, this number choose that number, choose K. So something like 5 choose 0 is 1. That makes sense. There's only one way to not choose anything. Then I need to multiply by some stuff. I need to multiply by what? Well, I need P to the K. So I need this cell to the power. So I use my caret symbol, shift 6, to the K power of that cell. So that's n choose K times P to the K. And then times 1 minus P. So I need a parentheses. 1 minus P and the parentheses. That's all to the power n minus K. So I need another parentheses, n minus K. Right. So I have my n choose K bit times P to the K times 1 minus P to the n minus K. I get 0.03125. That's just kind of a coincidence that it looks kind of similar to this one, just because 5 choose 3 equals 10 and 5 choose 0 equals 1. So that's why they're off by a factor of, and because P equals Q. So they're off by a factor of 10. But that's kind of a coincidence. If I try to drag down, I see that it's not happy with that because up here I'm using the right N and P cells, but down here my N and P cells have shifted. So I want to take D1 and G1. Anywhere I see those, I'm going to lock them. So I'm going to select this D1 and hit F4 to lock that cell. Remember that sometimes we want to lock a cell so that when we drag down, that cell is always referenced exactly. And sometimes we want the reference to stay relative, like the K, for instance, when I drag down, I want my next line down, I want to refer to K equals 1, and the one after that to K equals 2. So I don't want to lock B4, but I want to lock D1 and G1 because I want to always refer to exactly those choices of N and P. Okay. And now when I drag down, it should work nicely. Let me clean this up a little bit. I'll go into my number tab here and just decrease the decimal places by a couple so they're all on the same scale. And I see there's about a 3% or so chance of getting 0 heads on 5 flips, and also about 3% chance of getting 5 heads on 5 flips. 15% chance of getting 1 or 4 heads, and about a 31% chance of getting 2 heads or getting 3 heads. So this does match with what I found over here. Probability of 1 head is 15.6%. Probability of 3 heads is 31.3%. But the nice thing is that with Excel, I just had to I had to type in the formula, which was a little more annoying than typing it into the calculator one time. But once I got the Excel formula typed in, I could just drag it down and it copied down very easily. Right? Each time I have to type this whole thing on the calculator, it takes a good bit of time. Now let's find my expected value. Oh, I guess I'll call it K times probability of K, probability X equals K. So I need to multiply these two columns together and then add them together. So I want to find my expected value here. Maybe I'll give that a color, say this kind of light green. And if I add these, I get 2.5. That's exactly n times p as we'd expect. Maybe I'll work my way towards finding the standard deviation as well. So what is the outcome squared? That's equal to this cell squared. I know I'm going a little more quickly through this than I have in the past, but since we've done this a few times on Excel already, I'm picking up the pace a little bit. Then I drag down. This gives me each of my outcomes, 0 through 5, squared. And my next column, that is outcome squared times its probability, or that's the cell in the E column times the original probability. Remember, we don't change the probability when we do this, the original cell in the C column. And we drag that down. Now this is going to give me the expected value of x squared when I sum this together. So we're not quite at variance or standard deviation yet. My variance is expected value of x squared minus the square of the expected value of x. So minus that cell squared. That gives me 1.25. What's my variance supposed to be? It's supposed to be NPQ. Let's check. What is equals N times P times 1 minus P. Exactly 1.25, right on. And my standard deviation, the square root of the variance, 1.118. And of course, that's going to be right if the 1.25 is right, but we can check it. Equals square root of N times P times parentheses 1 minus P. Close both of those sets of parentheses and we get exactly the right thing. So we got our calculated parameters, the mean, the variance, the standard deviation, kind of calculating directly from the probability distribution. And we saw they matched up perfectly with our formulas. I mean, of course, we derived these formulas carefully, but we do see that they match up. One thing I might notice about this is that this distribution over here, let me give it a nice color, maybe blue. There we go, something like that. So you can still see it pretty easily. I guess I'm feeling springy today. I'm picking like pastel blue and pastel green and bright yellow. Has felt springy this past week. But we look at this distribution, we might actually realize that these first three probabilities, 0.031, 0.156, 0.313, are just kind of the mirrors of the last three, 0.313, 0.156, 0.031. And that has to do with two things. One is that choose combinations are symmetric. Remember, with permutations, I kind of had like one group that I'm pulling off that's going to be ordered, where order matters, and then the other ones that I kind of leave in the bag where order doesn't matter. So they're different. But when I'm choosing, I'm just kind of like picking some out of the original bag and tossing them into another bag. I'm just deciding how to split the things between the two bags. If I pick, say, slots or trials 1 through 3 from the second bag and put them in the first bag, that's the same as picking slots 4 and 5 or trials 4 and 5 from the second bag and putting them in the first bag. Either way, I just end up with 1, 2, 3 together, 4 and 5 together in two different bags. So this combinations idea, it's a symmetric idea. So getting 0 heads on 5 flips versus getting 5 heads on 5 flips. Well, that's just getting 0 tails on 5 flips. The other thing that contributes to the symmetry is the equal likelihood between heads and tails, that P equals Q. One interesting thing you may have noticed here is the P to the K, Q to the N minus K, always just combines together to give me 1/2 to the 5th power. Because P and Q are the same number, 1/2 for each of them, those 1/2 to the K combined with the 1/2 to the N minus K to give me 1/2 to the K plus N minus K, or just 1/2 to the N, 1/2 to the 5th. So it's 1/2 to the 5th is the kind of probabilistic component everywhere, and the counting component. N choose K is symmetric, has this nice symmetry, this kind of bookend kind of symmetry. And there we go. We've got a nice symmetric probability distribution when our heads and tails are equally likely. What if my probability of heads was not 0.5? What if I was dealing with an unfair coin? What if probability of heads was 0.7? This is where Excel really shines, is if I want to do an experiment like this and say, do I maintain this symmetry if I break the symmetry in the probabilities? Maybe I still do get some symmetry, maybe not. Well, now I can just change my P equals 0.5 to 0.7, hit enter and see what happens. Right, I can change this because I referred back to this cell instead of hard coding in, 0.5 to the 1 times 0.5 to the 4, whatever. I refer to this cell. So I can change this cell, hit enter, and it cascades through the entire sheet. And it kind of looks like I've lost my symmetry. That makes sense because now getting 0 heads, when heads is a pretty likely occurrence, getting 0 heads on 5 flips is quite unlikely, but getting 5 heads on 5 flips is more likely. It's not so unusual. So it does make sense that I kind of break my symmetry here. But it kind of turns out that, roughly speaking, if P isn't too large or too small, if it's not too close to 0 or 1, and if N is relatively large, probably quite a bit bigger than 5, I still do like almost maintain a type of symmetry about the expected value. This N isn't quite large enough, and this P is a little bit too high to really maintain that symmetry in any kind of reasonable way. We were just taking this as a small problem, but if N was like 30 or 40 and P was like maybe 0.6 or 0.35 or something, I think we would see that there's a nice bit of symmetry here as well. Symmetry about whatever the mean ended up being. We do see also that the mean changed, as we'd expect. 5 flips, probability of heads per flip 0.7, so 0.3 or 3.5 as our expected value. And our standard deviation stayed pretty close to what it was, but it went down a little bit. Instead of about 1.12, it went down to 1.02. Remember, the highest variance in standard deviation is going to occur at a 50-50 coin flip. We discussed that as well briefly in an earlier lecture. So even if I went down to like P equals 0.3, I'd still see my standard deviation go down from 1.11, right? Or if I went to like 0.1, it goes down even further. My standard deviation is going to be highest whenever P is 0.5. So this is another thing that Excel is super nice for. It's just if I want to explore this kind of space of binomial distributions, I want to see what are some things that I maybe see at first glance on one particular distribution, and then does that cascade to other distributions as well? Does that is that characteristic kind of is it unique to this particular member of the family of distributions, or is it general to the whole class? And things like the symmetry are kind of unique to this particular choice where we have equal likelihood between success and failure. If we had worked with a larger N, we might have seen that that symmetry does hold a little bit more in an approximate sense for some larger N's and p's that are, not exactly 0.5, but not too far away. So Excel lets us kind of play around with these kinds of things in a sandbox kind of environment and get very quick answers to almost like experiments if we want to try it. Okay, so let's look at a second example in binomial distribution. So suppose we have a quiz with 10 multiple choice problems, and there are 5 options per problem and exactly 1 correct option for each problem. And let's look at 3 scenarios. Let's suppose that a student picks randomly. A student, hasn't attended class, they haven't read the material, haven't done any homework, they have no idea what's going on. So they sit down to this multiple choice test and they just pick randomly. What's the mean and standard deviation of the number of correct answers? And then what's the probability they get 8 or more correct? Okay, well, I see that if there are 10 questions, I have a fixed number of trials. There's each trial only has 2 outcomes. They can either get it correct or incorrect. There's a consistent probability of success. They pick randomly, and there are 5 options, one of which is right, so 20% chance of success on each trial. And let's assume independence. Maybe the student, could start putting things together, almost like use the test to take the test, hey, this piece of information in the problem was included in the problem statement, and that helps me answer maybe a different problem. But let's suppose that that's not really feasible for this test. So this fits the scenario of a binomial distribution. We're counting the number of correct answers.
Sir, I have a question.
Yeah.
So
Yeah.
if there are 5 options, is it like there is 1 correct and 4 incorrect?
Yep. Exactly. 1 correct option for each problem. Yep. And then 4 of them will
But
be
in
incorrect.
that case, there will be like 5 outcomes, or I mean, to fit into the binomial distribution, we need exactly 2 outcomes. So
Yeah. So the outcome is correct or incorrect. So whenever we do P, this would be probability that they get it correct would be 1/5 or 20%. And then 1 minus P would be the probability they get it incorrect, which would be 4/5 or 80%. So these are the two.
okay,
Just
so there is
crossing that.
not condition that both probability be 50-50. That's not the condition.
No, it doesn't have to be 50-50. Nope. Yeah, so just like over here, we could look at a coin flip where, say, probability of heads was 0.7. This is kind of like a coin flip where like probability of heads is 0.2. We can kind of imagine it being that way. Right? If the student just kind of randomly picks 1 of 5 answers and 1 of 5 is correct, the probability that they pick the correct answer is 20%. So it's almost similar to this kind of a distribution. Now we have a different n here, so it's not exactly this one, but it's a similar idea. Yeah, so that's an interesting point, is that we're overlaying one structure on top of another. So I'm trying to select this here and it's not cooperating, but we're overlaying the idea of a correct answer. So we're counting the number of correct answers. So an answer can be either correct or incorrect. There are 5 options per problem. So each of the choices, so the student picks A, B, C, D, E, each one of those is equally likely to be the correct answer from the student's perspective. But their probability of choosing a correct answer is 1/5 or 20%, and probability of choosing an incorrect answer is 4/5 or 80%. So this is our dichotomous outcome: correct answer or incorrect answer. Now, if we were like, if we were doing something where like, say we have 5 answers that are I mean, I don't think anybody would set up a multiple choice quiz this way, but just for example, if we chose to make a multiple choice quiz where like there are 5 answers and they each have some degree of correctness. Like one answer is more accurate than another, and that's more accurate than another, and so on. And we said, okay, I'll give you 1 point if you chose the least accurate answer, and 2 points if you chose the next least accurate, and so on, and 5 points for the most accurate answer. And then we were going to add up the points for all of those. Well, now we don't have a binomial distribution because, each answer could be 1, 2, 3, 4, or 5. So now there's 5 choices for each answer. But here it's just basically like you either get 1 point or you get 0 points for each of your answers, or you either get it correct or you get it incorrect. Yeah, so that's a good question, and because we're just looking to count the number of correct answers, the options are each answer was either correct or incorrect. There's no like gradation of correctness. Or if we weren't looking at a multiple choice problem, if we were looking at, a problem on either our exams on my stat lab or, even more clearly like a written exam in a class, in an on-campus class, then there's things like partial credit and all of that, right? There's a different score that there's a variety of scores you can get for each answer. And now all of a sudden it's not binary. It's not correct or incorrect. You could get a low score or a medium score or a high score. Yeah, so that would not be a good situation to model with a binomial. But in this case, it's the correct versus incorrect that we're looking at as the two options. So we see that P is 20% probability of a correct answer. And there are 10 problems, so there are 10 trials, there are 10 attempts. So n equals 10. And we expect to get NP, or 10 times 0.2, or 2 answers correct out of the 10. And with a standard deviation of root NPQ, 10 times 0.2 times 0.8. And let's jump over here and do that. So 10 times 0.2 times 0.8 is 1.6, and that's our variance, and let's square that. Square root that. I think I said square that. So that's about 1.26 or so. So what's the probability they get 8 or more correct? I can actually answer this really easily. My mean is 2. My standard deviation is a little over 1. To get from 2 to 8 is what? Something like 5 or so standard deviations? What's the likelihood of getting a 5 sigma event, a 5 standard deviation event? Extremely unlikely, right? So getting 8, 9, or 10 correct, what is 8 minus the mean of 2 over the standard deviation of 1.26? Oops, forgot my equal sign. So you can see just under 5 standard deviations above the mean. We know that's going to be essentially 0. But let's actually compute it and check. So this was our variance, and this was our standard deviation. And let's do something similar to what we did up here. So of k, the number of correct answers, and this could range from 0 to 10. So I'll type 0, 1, and then a little kind of trick is you can just copy this down if you select the 0 and 1. And Excel is smart enough that it will say, okay, you started with 0, 1. I think you want to just keep progressing. And it'll let you copy down, and it'll just keep incrementing that number. Now let's do probability x equals k. Well, I know that n is 10. And I know that p is 0.2. So up here, I wrote out my formula kind of longhand, so to speak. I wrote out n choose k, p to the k, q to the n minus k. That was a good bit of work. We actually can lean on Excel even a little more here. Excel knows about the binomial distribution. So if I start typing in binomial, B-I-N-O-M, I see I have some binomial distributions here and returns the individual term binomial distribution probability. For this first one, binom.dist. I'll choose that one. I'll hit tab. Now it asks me what's my number of successes I'm interested in. That's k. 0 in this case, or when I move down 1 or 2 or 3, comma, what's the number of trials? Well, that's n. I better lock that cell because I'm eventually looking to drag this down and I want that to be exactly that cell. What is it? E20 every time. What's the probability of success? That's 0.2. And again, I better lock that with F4 because I want to refer to this exact 0.2 cell every time. I don't want that to change, comma, and cumulative. I do not want the cumulative distribution. I don't want probability X less than or equal to K. I want probability X equals K, so false. I want the probability mass function, not the cumulative distribution function. And if I click and drag down, I do see that the probability of getting 8 answers correct, basically of getting a B or better, is, well, probability of exactly 8 is something like 10 to the minus 5, or 9, 10 to the minus 6, 10, 10 to the minus 7. So something in the ballpark of 1 in 10,000 or so, 7 times 10 to the negative 5, being added to numbers that are even less than 1 in 10,000. For all intents and purposes, you're not going to get more than 8 or more answers correct by just guessing on a quiz like this. Right, so what's the probability X bigger than or equal to 8? It's the sum of these three. Right, 10 to the minus 5. Okay, let's look at scenario B now. So now let's suppose that a student knows a bit about the material. They can narrow down the choices for each of the 10 problems to 3 possibilities, but they pick randomly between the 3. Right? Most multiple choice quizzes, there's kind of like 1 or 2 throwaway options, and then there's a couple of, solid contenders for the answer. So for this one, for each of the 10 problems, essentially they have a 1 in 3 chance of getting it right. What's the mean, the standard deviation, and the probability of getting basically a B or better. So let me come up here and change this around a little bit. My expected value of X I'm going to write as equals N times P. So I'm going to change that around. And my standard deviation equals square root of N times P times 1 minus P. So these numbers and this one, these are what I'm interested in when I'm trying to answer this question here. So here N is 10. We're still looking at a quiz with 10 problems. But they're able to eliminate a couple of options from each answer, giving them a 1 in 3 chance. So something like 0.333 for the probability of success for each answer. And how does this change things? Well, now their expected number of correct answers is 3.33 with a standard deviation of about 1.5. What's the chance they get 8 or more correct? Well, 8 is still quite a ways, quite a few number of standard deviations from this expected value. So every 2 standard deviations is about 3 units. So I'm about maybe 3 standard deviations or so above the mean just to get to 8. Right? If I want to do that calculation What's the z-score for 8? Equals 8 minus the expected value over standard deviation. So about 3 standard deviations. Is it likely that I get a 3 sigma event, that I get an outcome that's 3 standard deviations above the mean? That's pretty unlikely. And we see that reflected in the probability down here as well. 0.0033, not a likely chance, maybe 1 in every 300 or so. Tries at an exam like this, they would get a B or better. Now let's suppose that a student has a pretty good idea of what they're doing. So scenario B is like, you attended classes, but you only attended half of them, and the ones you did attend, you slept through half of them, but you can kind of, put together a little bit of enough to get rid of the silly answers, but that's about it. So this student's not going to get a good score either. What about scenario C? Let's suppose, this might be a student who's attended class, done the homework, is kind of at a moderate level. So suppose they know the answer to 5 of the problems. So for 5 of the problems, that's a known success. They got the correct answer for those 5. For the remaining 5, they can narrow down the possibilities to 2 choices each, and then they choose randomly between those 2. Now, what's the mean standard deviation of the number of correct answers, and what's the probability they get 8 or more correct? Well, now if I look at the number of correct answers, maybe I'll call this variable n, number correct out of 10, n is kind of like 5 plus x. There's 5 that they're going to get right. They know those ones. They know those answers. There's let's just say 100% probability they get those right. There's, nearly 100% probability they know those ones. But this x is the random part. They're guessing on some other of the questions. They're guessing on 5 of them. This is what we want to model with a binomial. So x is going to be binomial. How many problems are they guessing on? Well, that's only 5 of them. And what's the probability of success per problem? Now they're able to narrow it down to 2 choices. P equals 1/2. So let me come back over here. I'm going to get rid of these down here. So these are the outcomes related to the 5 that they're guessing on. They're guessing on n equals 5 of them, with probability of success of 0.5 on each one. I haven't adjusted my blue formulas yet, so don't. So we're getting there. What's my expected value of n? Well, that's expected value of 5 plus x. But that's just the expected value of 5, or that's just 5, plus the expected value of x. So my expected value of the number correct out of 10 is actually going to be 5 plus n times p, where n is 5 and p is 0.5. Now their expected number correct is actually 7.5. We're getting pretty close to 8. It's not going to be unlikely that they're going to get 8 or better. What's the standard deviation? Remember, the variance of n, or the variance of 5 plus x, the variance doesn't care about the location. All the 5 plus does is change the location. It doesn't change the spread. That's just the variance of x. Or square root of npq, square root of n times p times 1 minus p. Interestingly, that variance calculation doesn't change. It's just the variance associated with the random component. The fixed component, the 5 that you know that you got right, doesn't have any impact on or doesn't increase the variance outside of what it is already here. So the only variance, the only variability or volatility comes from the ones you're guessing on, not the ones that are the sure thing, of course. What's the probability that, in this case, we want n bigger than or equal to 8, let me do this in a different color over here, n bigger than or equal to 8 means that 5 plus x bigger than or equal to 8 means that x bigger than or equal to 3. So what's the probability that x is bigger than or equal to 3, or that the total number correct is bigger than or equal to 5 plus 3? Well, that's the sum of these three probabilities. I have the 5 in the bag that I know I got correct. And then what's the chance I get 3, 4, or 5 more correct out of the ones I'm guessing on? That's what I would need to get an 8 or larger, 8, 9, or 10. That's actually 0.5. I again see the symmetry from the probability being 1/2, getting a success or failure in each one. The symmetry coming from that, turns out I have a 50-50 shot at getting 8 or better. And we can see that that's not an unlikely thing to occur. We're only half a standard deviation above the mean. And really because our mean is kind of like a continuous feeling thing, but we're dealing with a discrete set of outcomes here, it's really kind of right in the middle. So 50-50 shot of getting 8 or better, getting a good grade on the quiz. If we know the answer for 5 of them, and for the other 5, we're able to narrow it down to 2 choices. And that seems kind of like, like a student who is moderately knowledgeable about this material. If they know half of it for sure, and the rest of it, they can make a pretty decent educated guess. They can narrow it from 5 choices down to 2. And it seems like that student would often get about a moderate grade. So these are the things that, if I was putting together a multiple choice quiz, I might start thinking about things like this. If a student doesn't know anything, what is their score likely to be? If they know a little bit, what is their score likely to be? I don't want those students to be able to just guess and get a good score. But on the other hand, I want to make sure that the students who kind of have a moderate amount of knowledge, even including guessing, will get kind of, a moderate score most of the time. With a moderate amount of knowledge, it's still unlikely the student's going to get 10 out of 10, and not all that likely that they're going to get an A, get a 9 or a 10 out of 10, right? Less than a 20%, less than a 1 in 5 chance that they're going to get an A, even with guessing, with a moderate amount of knowledge. And that feels about right. It should be unlikely for them to get an A, but also, pretty unlikely for them to get, say, a D or F as well. So any questions on binomial theorem, binomial distribution? All right, let me switch my screen share here. Close down some of these other windows. Okay. Sorry, my OneNote's starting to get a little laggy. I'm trying to change the window size here to make it show up a little better for you, and it's being a little jumpy. There we go. I think everything is looking good now. All right. So I just wanted to focus on this window because we're not going to be using Excel as much in this next part when we talk about Bayes' theorem. So this makes it a little bigger on your screen, a little easier to see. Okay, so like I mentioned, section 5.3 on Poisson distribution. I'll post the YouTube video as a supplement for that. And we're starting Bayes' theorem. There are some extra notes on Bayes' theorem posted on Blackboard under the supplemental materials folder in the chapters 4 and 5 subfolder. So you can take a look in there for kind of a bit more extensive write-up than the book has. and for kind of some notes to go along with the lecture and some extra practice problems. All right, so we'll start with a motivating example from Bayes' theorem. So suppose there are two car manufacturing plants. We'll call them plant 1 and plant 2, or just P1 and P2. And that each produces the same two car types, type 1 and type 2, we'll call T1 and T2. So this might be like, Toyota producing cars in two plants, maybe like Detroit and Georgia or something. I don't know where their plants are, but and that they produce the same two car types, let's say, Corollas and Camrys. Now, suppose that we know that of the cars produced by plant 1, 10% are type 1 and 90% are type 2. So maybe 10% are Corollas, 90% are Camrys. And suppose that of the cars produced by plant 2, 95% are type 1 and 5% are type 2. Maybe of that plant, 95% are Corollas, 5% are Camrys. And then suppose that when these cars are shipped out, they basically end up on the car lots just basically mixed together. It's not more or less likely that, not necessarily that, you're going to get that this car is going to go to that dealership or the other dealership or something. They randomly get mixed together, sent out to the dealerships, and end up on lots for sale. Now, if we walk onto the lot, and let's say for some reason this car lot has all of the cars covered up, and I point at a car and I say, okay, that car, what's the probability it came from plant 1? That's one question I could ask. But then maybe they uncover the car and I see that it's a Corolla, that it's a type 1 car. So we walk onto the lot, we observe a car, and we have identified that it's a type 1 car, maybe a Corolla in this case. We could ask, what's my guess about the probability that the car came from plant 1? In other words, what's the conditional probability the car came from plant 1 given that it's of type 1? Do we think this probability is going to be high, moderate, low, or do we need more information to make any kind of a decision here? Now, a lot of people would look at this and say, well, given that I know the car is type 1, plant 2 produces a higher ratio of type 1 cars than plant 1 produces type 1 cars. So I think it's going to be likely that it comes from plant 2 and probably unlikely that it comes from plant 1. This is what a lot of people would say because, if you look at the cars coming off of plant 2's assembly line, lots of those, a large proportion of them are type 1, versus you look at the ones coming off plant 1's assembly line, a smaller proportion of those are type 1. So being a type 1 car fits better with plant 2 and doesn't fit as nicely with coming from plant 1. So maybe we would estimate a low probability of coming from plant 1 given that the car is of type 1. Right, we want to find probability of plant 1 given type 1. Now let's think about this for a minute though. So suppose that there are a certain number of cars made, how many came from each plant? Well, we don't actually have any information on that, do we? I mean, if it's an extreme case, plant 1 might be shut down for repairs, right? I think there was wasn't there some kind of car manufacturer that was like hit by a hurricane or something and like was shut down for a long time? I think that North Carolina hurricane like messed up a lot of manufacturing stuff, but if plant 1 was shut down for repairs, the probability would be 0 because like at this point, none of the cars in the lot are from plant 1, they're all from plant 2. On the other hand, if plant 2 was shut down and plant 1 was the only operational one, then it would be 100%, right? So we see that this piece of information about how many cars is each plant producing is actually a really important piece of information. And the two extremes, this probability that I maybe initially estimated as low could be anywhere from 0% to 100% or seemingly anything in between. Okay, so we might have estimated low, but now we're thinking, okay, if I look at the extremes, this makes me question this estimate. And a lot of people would estimate low. There's a what was his name? I think David Grether. His last name was Grether. There's a paper where this guy Grether did some experiments of kind of this type, giving people scenarios like this and asking what they thought the probability of something was, high, moderate, or low. And, you know, people, it was quite likely that people were just ignored an important piece of information in favor of, things a little bit more surface level like this, like plant two, producing lots of type 1 cars just fits better with this being a type 1 car. So I think it's likely they came from plant 2 and unlikely from plant 1. But what's going on here? Like, why isn't this 95% versus 10% just the end of the story? Well, what is this 95%? This is actually probability of a type 1 car given, plant 2. And this is probability of a type 1 car given plant 1. But actually, that's the reverse condition of what I want to know. So a lot of people will say like 10% is low. So probability of plant 1 given type 1 has got to be low. But really 10% is probability of type 1 given plant 1, not probability of plant 1 given type 1. The condition is reversed. And we actually have to be really careful here, right? It might seem like if we reverse the condition that like, well, what does that do? Can that really have that big of a relationship? We're still kind of relating the same two things, but actually it can have a significant relationship. Okay, so let's go through this kind of by brute force before we develop Bayes' theorem. Okay, so let's suppose that there are a total of 200 cars made overall. And further, let's suppose that of all cars, plant 1 is a much bigger plant, so it produces 90% of all cars, and plant 2 produces 10% of all cars. Plant 1 is 9 times as big as plant 2. So on one hand, if I just walked onto the lot and the car was still covered up, and I asked you, what's the probability this car comes from plant 1, and you don't know which type it is, you would actually say 90%, right? Because I know that plant 1 is the much bigger plant, it's more likely to have come from plant 1. But then I have this kind of countervailing factor that of the cars that plant 1 produces, a smaller proportion of them are actually type 1 cars. So that kind of leans me a little bit away from plant 1. So there's actually two forces in play here. Kind of the likelihood of plant 1 kind of overall versus the maybe in some sense kind of like subjective or conditional likelihood of plant 1. So that's really there's kind of a tug of war going on here. So if plant 1 produces 90% of the cars, and if we have 200 cars, then 180 cars came from plant 1 and 20 from plant 2. So if we draw kind of a tree diagram here, we have plant 1 or plant 2, and there are 180 cars from plant 1. Of these 200, and 10% of the 220 coming from plant 2. And then of the plant 1 cars, some are type 1, some are type 2, and of the plant 2 cars, some are type 1, some are type 2. Of the plant 2 cars, 5% are type 2, or 1/20th are type 2, so an average about 1 out of those 20 coming from plant 2 are also type 2, and 19 of those 20 are type 1. And from plant 1, 10% are type 1, so 10% of the 180 are type 1, or 18. And 90% of the 180, or what would that be, 162, are type 2. Now, what do I know about the car? I know that it's type 1. It's given type 1. What's the probability of plant 1? So I know that my car has to have come from one of these two scenarios, the car that I'm looking at. And these are all equally likely. So the number of type 1 cars that kind of made it out to the dealer's lots that I could be looking at are 18 plus 19. And what's the number of those that also came from plant 1? 18. So my probability is actually 18 over 37, or pretty darn close to 50%. What's 18 over 37 is 48.6%. So actually, it's a moderate probability. What can we learn from this? Well, two things. One is that there's this very important piece of information that's kind of the overall likelihood, in this case, say, of the two plants, of a car coming from plant 1 versus plant 2, or just kind of the overall prevalence of a characteristic in a population, is very important in these kinds of scenarios. And the second thing is that we have to be very careful about which way our conditions are going. Really, what I'm trying to do here is I'm trying to answer a question about the conditions one way, plant given type, when I have information that's presented the other way, type given plant. And you might look at this and say, oh, maybe this is just a silly mathematical example, or this doesn't really come up in the real world, or whatever, like, or it's just one of those like philosophical paradoxes, like the ship of Theseus or something. But it's actually much more ubiquitous than you might think. And we're going to see several examples dealing with Bayes' theorem and the Bayesian way of thinking that I think by the end of this, hopefully you'll agree that this is actually a practical problem in a sense, and it's something that we really need to at least understand exists when we're interpreting really evidence in favor or against almost anything in the real world. Okay, so for this one, we kind of, worked through by brute force, just with, suppose there are 200 cars made, and how do those cars cascade through this little diagram here? But let's come up with something that's a little more abstract so we can apply it a little more readily. Let's come up with a theorem. So what is Bayes' theorem? Bayes' theorem says the following: probability of A given B equals probability of B given A times probability of A over probability of B. Let me actually bump this down to the next line. There. That just makes OneNote displayed a little bit bigger for you. So probability of A given B, the condition here is given B. And on the other side, I have probability of B given A. I get to flip the condition. However, when I flip the condition, I have to multiply by the ratio of probability of A to probability of B. What is the proof? It's actually just a one-liner. Note that the and conjunction is commutative, so A and B is the same as B and A. So probability of A and B can be written two ways. Just by our multiplication rule for dependent events, probability of A times probability of B given A, or probability of B times probability of A given B. And then we just solve for probability of A given B by dividing both sides by probability of B. So probability of A given B equals probability of B given A times probability of A over probability of B. If we apply Bayes' theorem to the previous example, what do we get? What we want to know something about is probability of plant 1 given that it's a type 1 car. What I have information about is probability of a type 1 car given plant 1 being 10%, or probability of type 1 car given plant 2 being 95%. So I want to know something about probability of plant 1 given type 1, but my information is phrased the other way. I can flip the condition, make it probability of type 1 given plant 1, provided that I multiply by probability of plant 1 and divide by probability of type 1, the overall probabilities of those characteristics. Now I have probability of type 1 given plant 1. That's my 10%. I also have the overall probability of plant one. Once I filled that in, that was my 90%. I don't really have an overall probability of type 1 because some of the type 1 cars are coming from plant 1 and some from plant 2. But I do realize that, let me just bump over to the side here, that a type 1 car is, well, it's either a type 1 car from plant 1, in other words, it's type 1 and plant 1, or it's a type 1 car from plant 2, type 1 and plant 2. And each of these, say type 1 and plant 1, I could break up with the multiplication rule. And I'll choose to break it up this way so that I'm conditioning on plant 1 because that's the information that I have. The information that's given to me is the information conditioned on which plant it is. So the probability of type 1 is probability of type 1 and plant 1. These are mutually exclusive events. We're presuming a car can't both come from plant 1 and plant 2 simultaneously. So this is plus probability of type 1 and plant 2. And we can see that probability of type 1 and plant 1, but the multiplication rule gives me probability of type 1 given plant 1 times probability of plant 1. And similarly for probability of plant 2, type 1 and plant 2. And I see that I get 10% times 90%, just plugging in the numbers for these from above, over 10% times 90%. Note that the numerator will always be one of the terms in the denominator. That's something that's true about Bayes' rule. We're looking for the proportion of type 1 cars that are also from plant 1 relative to the proportion of all type 1 cars is really what we're looking at. Because what we know about the car is that it's a type 1 car. I can forget about all the type 2 cars now because I know it's not a type 2 car. But I get 10 times 90, 10% times 90% over 10% times 90% plus 95% times 10%. Here, I've just noted that percent squared is in all of my terms on the top and bottom. It can just divide out. So instead of writing 0.1 times 0.9, all these points everywhere, then I might make a mistake typing into the calculator or whatever. I just got rid of the percents. And I noticed that I have probability of type 1 given plant 1 is small versus probability of plant 1 is large. But compared to that, I have probability of type 1 given plant 2 is large compared to probability of plant 2, the overall probability is small. Those are my two countervailing forces. I have one large and one small on one side, and I have the other one large and the opposite one small on the other side. There's more of a tug of war than we may at first have realized. If we were just looking at the 10s versus the 95, that's only one part of the equation. This gives us, again, 18 over 18 plus 19, or about 49%. Okay, I think that is all I have to say about that. So we can use Bayes' theorem directly to get us the answer, and this is the approach that we're going to take for most of our problems from here on out. I really don't want to try to find like basically a least common denominator kind of deal where I can cascade a number through all of this and draw these pictures out and everything. That's going to become pretty complicated pretty quickly when we get to other types of problems. Okay, so why are we spending so much time on this one theorem? I mean, we didn't talk this much about the multiplication rule or the addition rule. This is just another little rule that we can use to flip a condition around, and that's the end of the story, right? Well, there are really two interpretations here. And one is that interpretation, and to be fair, that is a valid interpretation. It's just a rule that tells you how you flip the condition around if your information is phrased this way and you want to know something in that direction. So it's a helpful little rule. You can flip the condition so long as you multiply by the ratio of the overall probabilities of the characteristics. Or another way of looking at it is, say, probability of A given B. So given that if we have a Venn diagram down here, given that we're in the blue blob, what's the probability of A? In other words, what's the proportion of the blue blob that is to the left within this A rectangle? So probability of A given B is this proportion. Given that we're in B, what's the probability of A? It's this proportion to the whole blue blob. And on the other side, probability of B given A. So given that I'm in A, given that I'm in the red box, what's the probability of B? So that also kind of refers to this blue blob. So the numerator is maybe somewhat similar. It's just probability of A and B for both of them, but it's really the denominator which changes. And that's why we have to multiply by this ratio of probability of A over probability of B. In a sense, we're kind of like getting rid of the denominator. We're getting rid of like probability of A and putting in probability of B in the denominator in some sense. So we can think about it this way. It's just this kind of graphical representation. It's just a little tool that we use. But there's actually a really significantly different way to think about it. And this is where the idea of frequentist statistics versus Bayesian statistics really, really kind of starts rearing its head. You might have guessed that it's called Bayesian statistics because it's based off of this Bayes theorem idea. I don't think Bayes ever thought about this little rule that he made in this manner. So it's kind of named after him. I don't think he even ever published the rule in his lifetime. I think maybe they found it like in his notes after he died or something. But it still bears his name. So what's another way we can think about it? So Bayes' theorem says my numerator is probability of B given A times probability of A. I can kind of pop the conditional probability off of the top and then look at probability of A given B changing to probability of B given A when multiplied by some kind of correction factor. But I could instead choose to pop the probability of A off the top and look at probability of A given B being related to probability of A times some correction factor. I haven't done anything mathematically stunning here or anything, but this just makes me maybe think about it a little bit differently. In other words, maybe I think about this as, well, I walk onto the car lot and all the cars are covered up. I can't see what types any of them are. I don't know whether they're Corollas or Camrys, the strangest car lot in the world, but whatever. And if I point to a car that's covered up and ask you, what's the probability that car came from plant one? You would say, well, 90% of all cars come from plant one. So that's your worldview at that point. We pointed at this car that's covered up. You don't know what type it is. So that's your estimate for the probability based on only the information about how the plant one and plant two, how pervasive their cars are in the market. But then we pull the cover off the car and you see that it's a Corolla. You see that it's a type 1 car. Well, now you have a new piece of information. How should you treat this new piece of information? You don't want to just go all in and say, well, because it's a type 1 car, that fits better with plant 2. So now I think it's, certainly plant 2. Because type 1 car fits better with plant 2 because of this number. We don't want to say that because that ignores our previous worldview. I mean, we had that worldview based on some evidence, based on, or for some reason. So we have a new piece of evidence. We don't want to just completely overwrite anything that we've previously known. But on the other hand, we don't want to just dig in our heels and we don't want to just ignore the new evidence. We don't want to just say it's 90%, period, end of story. I don't care what new evidence you give me. I want to systematically incorporate this evidence so that I simultaneously respect my previous worldview, which was built on other pieces of evidence, but also take into account this new piece of evidence. And that's how we can view this. We can view what's my estimate of the probability of event A. I have some estimate of that, and then I observe B. I observe a new piece of evidence that event B has occurred that maybe impacts my going forward, my estimate on probability of A. So I observe that it's a type 1 car. How do I systematically incorporate that new evidence with my previous evidence to give myself an updated worldview that respects both pieces of evidence in a systematic way? We use Bayes' theorem. Right. So one point of view is this is just a trick to flip the condition, but the second point of view is we're updating a worldview based on a new piece of evidence. So that's the two paradigms, the frequentist versus Bayesian idea. Frequentism doesn't really allow for this kind of an idea. A frequentist philosophy would say, well, event A is event A and probability of A is probability of A, like regardless of what new piece of evidence you have. So frequentism doesn't look at these kind of population parameters as being flexible or being estimates. But Bayesianism or subjective probability looks at them as being something like degree of belief. And this is really where the nuance comes in with probability, right? Both of them would agree on all of the math stuff, right? Frequentists would agree with this statement, and so would Bayesians. You know, the frequentists and Bayesians would agree on the chapter 4 stuff or the chapter 5 stuff. There's no dispute there. The mathematical structure is not what's disputed. The question is, when I take this mathematical structure, when I do this, and I overlay it onto something in the real world, and I choose to model something in the real world with this probability structure, what am I saying about what happens in the real world? The frequentist is always saying something about, well, frequencies. They're saying something about if I repeated this process 100 times, kind of on average, how many times would this or that happen or something like that. The Bayesian is saying, you know, in many cases, I can't repeat the process 100 times, right? If I have some ailment and I go in and I have to choose between 3 medical treatments, I can't just do that 100 times. I need to pick one and go with it. So when I say the probability that this is successful versus that is successful, that means a very different thing. I don't get to average over 100 trials. On the flip side, maybe my doctor actually does get to average over 100 trials, right? If my doctor sees 100 patients with this ailment and they give different medications, maybe they do get to say, like, you know, if my success rate is 95%, I'm happy with that because I feel like that's a better success rate than they would have gotten not coming to me, or they would have gotten going to kind of, you know, another random doctor or something. So kind of from the doctor's point of view, they do get to maybe adopt more of a frequentist perspective. But from the patient's point of view, it's kind of like, you know, you're an N of 1. It's either going to work or not work for you. So then probability maybe should be interpreted in a manner that's more like, how much do I believe that this is going to work for me? So when we come back, we will look at example 1 down here, testing for cystic fibrosis carrier status. And there's a little bit of medical background that we'll need to talk about. So we need to talk about, like, what is autosomal recessive and some of this stuff. But what we're going to look at is fairly essentially realistic numbers for what we call the prior probability of a carrier, of someone being a carrier. So before any medical test is done, just understanding their family history and how genetics works, we might estimate that this is their probability of being a carrier based on, say, a sibling with CF. But then we run a genetic test for carrier status. The test comes back indicating that he's a carrier. But again, like, or sorry, the test comes back indicating that he's not a carrier in this case. We don't want to just forget about our prior probability that was, on the basis of family member being a carrier, this being an unlikely disease, and so on. We don't want to just jump right over to the test result and say that that is 100% accurate all the time. Tests are never 100% accurate. But we also don't want to just ignore the test. We want to incorporate the results of the test carefully in with our previous knowledge and come up with a posterior probability distribution of being a carrier. So that's what we're going to look at here. And really, any of these medical testing and diagnosis type problems, really Bayes' theorem is hiding in the background. We have some index of suspicion for a certain disease. We do a test, and that changes the index of suspicion up or down. The tests are almost never 100% one way or the other. So that's what we're going to look at next time. So I think Bayesian stats is something that really warrants a couple of lectures, especially because it applies, it applies so often to things in the medical world, things in the finance world. We'll see a machine learning example, so kind of the CIT world. So Bayes' theorem, very important ideas. It's a bit of a deviation from our usual trend of sticking to frequentist statistics, but I think it's a valuable one to at least introduce and understand a little bit of, so we have maybe a more full understanding of when we take this probability model material and apply it to the real world. One way to do that is through, say, confidence intervals and hypothesis testing, but another way to do that is through the kind of Bayesian perspective. And they're two different camps on how this should be approached. Okay, let me stop the recording.